Okay, it will take me just a minute to get this set up. So what we're going to do today, let's go ahead and get started. So we're going to talk about the LCD display, and unfortunately I left my junk drive in my office, but I think I have it on Okay, so how many of you have already started on your projects? Why right, we still got 3 weeks, so why bother, right? Well, actually, so currently it's scheduled for the 11th, but I'm looking to change it to the 18th. Just because I sense that there's been a lack of progress. Yeah.
It's going to be helpful to use this lecture. Most of us working with the display will have more time to.
Yeah. Got it.
Have that for like 8 weeks.
Yeah. So that's what I'm working on. So if the atrium's available, we'll change it. And I'm waiting to hear from Justin. So I'll let you know as soon as I hear. All right. So if we look at the syllabus, currently. So currently, we're looking at the 11th, but like I say, I'll try and change that. So here we are on the 19th, and we're demo LCD display. So I'll do that and talk about LCD displays. This week in lab, we're gonna do the photoresistor. Let's see, did we do? So before break, we did read the temp sensor, but we read the on-chip temp sensor, right? And then we did and we displayed it through the UART with the terminal window, right? We did that? Okay. So this week we'll have a little plug-in module that has a built-in temperature sensor on it, and it also has a photoresistor, and we'll have you use the photoresistor and the temperature sensor in Lab 8. It'll also be use the analog to digital converter, and I think we're also going to use the UART, the TTL UART USB to display it in the terminal window. But I'll talk about the lab on Thursday. Okay, so then on Monday next week, we'll review for the practicum, and then a week from this Thursday, we'll have the practicum. And again, I still am thinking about that. I haven't totally decided just exactly what to do, but generally, for sure, it'll involve you bringing your board to class with your laptop, your IDE on the laptop, and what I want you to do is you'll get a sheet. I want you to form up into teams of 1, 2, or 3 students. So you can use your same project team if you want, or a different one, whatever. And when you form up in those teams, then the first thing you have to do is every individual. So if you have a team of 3, then you have to have 3 Viva boards put together. They have to be the black ones, and you have to have a blink routine running on the board. So I want you to make sure you preload it with a blink routine, so when you come in, all you have to do is power it with your battery, or with a USB cable plugged in, or with your with the 2103 cable. Well, maybe we'll bring some of those to class. And once you power the board, then it starts blinking, and as long as I go by and see, then you get checked off. That's 10 points. Then the other 90 points, I'll give you a sheet that basically will have, on that sheet it'll have a set of requirements, and then everybody in the class, or every team of 1, 2, or 3 people, so you can work by yourself if you want, with 2, with 3, every team will have a slightly different problem. And what you'll basically have to do is code that up and demo it. And as soon as you get it ready to demo, we'll take a look at it, and basically you'll get credit or not, depending on whether you checked all the squares. If you'll get partial credit if you got part of it, and if you didn't get any of it, then there'll be some sort of minimal score you'll get. But anyway, but the idea is I want you to write the code. Yeah?
Is there a specific blink routine you want to load up?
No, anything that makes the LED blink, any one of the colors blink is fine. Yeah. Just show that your board works, basically, and that it's programmed with something. You don't have at least if you don't have a programmer, make sure you combine in a group that does have a programmer. So somebody in the group's got a PicKit3 or a Snap. And if you're going to use a Snap, make sure that all of your Viva boards aren't configured with low voltage programming turned off so that you wouldn't be able to program. So make sure you turn low voltage programming back on. It turned out that was a very interesting thing. You know, for years it was kind of better to have it off, but now it's kind of better to have it. I mean, yeah, it was kind of better to have it off, and now it's better to have it on. So who knows? Kind of, it's a little bit strange the way it sort of all played out. But anyway, now it's definitely better if you have low voltage programming turned on. So what I'm going to do is get set up here. So I have a little thing called an Electronic Explorer. It's a little Xilinx board that is. It's actually very nice because it gives us this ability to control a bunch of digital I/Os all at once, and so that's kind of cool. And so that's what it looks like. And sitting in the middle of this is a 16:2 LCD display. I can turn the light on. You can kind of see it sitting there. Right now, the board's powered up, but the power supply and none of that's turned on. And so what we have to do to make it work is we have to bring up the software. And so I have that. So I have that set up here on my laptop, right here. And so here's it set up, and so it has built into it a whole bunch of instruments. It's really a very nice little thing. There is a student thing. So if you go to there's a 2-channel. I don't know. I think it's a 100 megahertz scope. It's pretty good. Wave generator. It has programmable power supplies. It's got a positive and negative supply that can deliver. Quite a bit. I forget how much. Maybe. I think it looks like it can deliver an amp and a half negative and something like an amp and a half positive. Then it has a fixed supply that can also deliver, I don't know, maybe several amps. And then it's got two reference voltages that you can use that can't supply very much current, but you can pick whatever reference voltage you want. And so we'll use one of the reference supplies for the contrast, and then we'll power the chip with the 5-volt supply, and then we'll also we'll power the backlight with the positive power supply. So we're using 3 of the power supplies, although you could probably just do it all with one power supply. And then it has voltmeter. Oops. So anyway, so it's a nice little gizmo here. All right, so I don't know where it's going to go. Oh. So it has a data logger. It has a logic analyzer. It has an arbitrary waveform generator. It has static I/O, and that's what I'm going to use. And then a spectrum analyzer and a network analyzer and a whole bunch of other stuff. I don't know. Anyway, I haven't used half of that. And it's the same software that works with the electronic with the I don't know. They have a couple of other products. I forget. It's the Digital Explorer and then Analog Analyzer 1 and Analog Analyzer 2. Anyway, but we're going to look at the static I/O. So here's the static I/O, and it has a total of 24 GPIO pins that you can drive as outputs or inputs. You can set them up as switches. It can be 0, 1, or high Z, or you can have them drive LEDs or whatever. You can have push buttons. So what I've set up here is 8 slide switches that can be 0 or 1 on the 8 data pins, and then 2 switches for the 3 switches for the control lines, the push button on the clock line, which is the E line, and then the other 2. So I'll go through that here. Let me pull up the slides so you can kind of see. So go back to this one. So a couple of things. So within the, we'll be doing, I think we're setting this up in one of the labs. I think that's right. And what we'll do, but many of you will want to use one of these displays for your project because it makes a really nice way to get data out, to a user. And these displays, these 2 9x16 displays are pretty widely used. I'll show you, I also have an OLED graphical display that you can use, and then there are these same LCD displays that have some graphics capabilities too. You can put them in graphic mode, or you can put them in letter mode, and then you can create your own characters, and people have even turned them into little miniature video games. Anyhow, so they're pretty useful, and you will still find them in a lot of products. They're out there in a whole bunch of forms. So let me download the PowerPoints. Let's see here. Let's see if I can get I don't know, I may not be able to. So the nice thing is I put on the Blackboard sort of some files, some header files you can use to drive this display that makes it, okay, here we go. Okay, so here's what the displays, so here are the control lines for the displays. Well, first let me show you. So they look like this, and I have one that's just like this. On the back side, they have these little blobs, and underneath this blob is an actual integrated circuit chip, where the bonding wires are connected directly to the printed circuit board. They call it blob on board, and then they cover it over with some epoxy so you don't screw it up. And that saves them having to pay for packaging. And in fact, some of the manufacturers, when they make these, they're trying to shave a few cents off each one. They'll actually buy them uncut from Microchip, or whoever, Hitachi, or whoever makes this chip. It's not Microchip, actually, probably Hitachi. And they'll actually saw the chips apart from the wafer. So they'll buy a whole wafer, and then they'll saw the chips themselves with a diamond saw or some kind of laser saw. They'll put the chips on here, they'll put the bonding wires on, and they'll put the blob on. And you can see they've got 2 of these on here, and that's called blob on board. And it's it's a very low-cost way to purchase integrated circuits, but it's a lot more. It requires some pretty fancy machines to do that. You clearly cannot do that by hand. Bonding wires are clearly, you're attaching it right onto a silicon die and then to a board, and the wires are super, super tiny and fine. Anyway, that's blob on board. So when we interface these chips, they all have the same set of interface pins. Every one of these displays is driven by the same basic Hitachi chip, this HD 44780. Now, not all the chips are made by Hitachi. There's a lot of knockoffs now, but they all work the same, which is really nice because the interfaces are then uniform. And once you kind of understand and learn how to use this chip, you can pick any of a whole variety of form factors of this LCD display and use that. It's really nice. And your code doesn't have to be changed much at all. It's very, very cool. So these Hitachi chips have this interface. They have power and ground, and then they have the rest of the pins. So power and ground here, and the grounds are on the outside. So the first pin is ground, the last pin is ground. And I'll talk about this. The last 2 pins, well, most of them have a 16-pin interface, but some of them do have 14-pin. They do make a few with no backlights, but I think that's kind of old school. Before we had a lot of LEDs, we used to use an electroluminescent panel for the backlight, and so those were kind of expensive and high voltage and sort of glitchy. So people basically made a number of them without backlights, but nowadays almost all of them have an LED backlight, and the backlight has its own 2 power and ground pins. But the rest of the pins are to drive the display. So power, so ground, power, and then you have essentially 4 control pins. VO, which is the contrast pin, and I'll show you how that works in a minute. And then you have the register select line, RS. You have the read W line, and then the enable latch. The enable latch is functionally a clock, but you only have to clock it when you want to latch in your command. And then you have 8 data bits, D0 through D7. Now, in 8-bit mode, you have to use all 8 lines. But in 4-bit mode, we only need 4 of the lines, and then we send the data in 1 nibble at a time. And most of the hookups are done in using 4-bit mode. And you have to actually put the display in 4-bit mode. And once it's in 4-bit mode, then you have to make sure you send 2 nibbles each time you want to send a byte. Otherwise, you get out of sequence and things get real screwed up. So those are the control lines. You can read and write the chip, but the only real reason to read the chip is to read the busy bit to see whether or not it's ready to take the next command. It is true, you can also read data that's what you've written to the screen. You can also read the position of the cursor if you want, and some other things. But there's really no point in doing that, because you should always know all that information, since you're the one that put all that information there. So there's really no reason to be reading it. Since you're the one that should have written it, you should know what it is. But I suppose some situation might arise where you might not know and you might have to read it. So you could find out where your cursor is, you could do other things, but generally you know where it is because you set it there. So the only real reason typically for reading it is to actually read the busy bit. And if you just put a big timing delay in, you can drop that out, which means you don't really need the read-write line to be able to set it high or low with a GPIO pin. You can just ground it and you're done, because you're always writing, you're never reading. So you can do an interface with as few as power, ground, plus, and then the contrast line generally is connected to a potentiometer. You don't generally have to have the microprocessor mess with this. Although you could if the microprocessor were going to change the contrast remotely or something. But other than that, you would normally just set this in a fixed manner. So then all you really need then is the register select line to sort between whether you're giving commands or data, the clock line, the enable latch essentially, and 4 data bits. And interestingly, you might think that if in 4-bit mode you'd use D0, 1, 2, and 3, but no, you use D4, 5, 6, and 7 for some reason. That's just how it is. So in 4-bit mode, the 4 lower bits, the lower nibble does nothing, the upper nibble is where all the action is. So anyway, so that's that. And if you happen to want to read it and you're in 4-bit mode, you also have to read the upper 4 nibbles twice to get the 4-bit, the 8 bits out. Okay. It comes in a whole bunch of different form factors. The classic one is 16 by 2 lines. So there's actually 2 lines that are displayed, and there's 16 positions for characters. The characters can be formatted a couple different ways, but generally you format them in a 5 by 7 dot matrix manner. And all the characters are already predefined inside the chip. But there are some spaces left over for, I don't know, 16 or maybe even 32, I can't remember. There are a few spaces left over for your own personal characters if you want to add them. And then besides the standard ASCII characters, there's, I think it's hiragana characters are also available, and a few graphics things to start with. The nice thing about these is, and they come in 5-bit versions and in 3-bit versions. So if you have the right voltage, you can directly interface it to the micro without any problem at all. If you have the wrong voltage, you have to make sure you get the right voltage to the display, and then you can run the micro on a different voltage, and the pins will all work fine. They're all 5 volt and 3.3 volt tolerant, and so is your micro, so everything's hunky-dory there. But you do need to make sure you don't power a 3 volt LCD display at 5 volts, you burn it up. And I have some of both kinds, and honest to God, you can't look at them and tell which they are, so you just have to run it at 3 volts and see if it works, and if it doesn't, you go to 5 volts. It's kind of a sad way to do it, and we do burn a few up doing that. I tried to keep them separate, but it's impossible. The nice thing is you can interface these directly to a micro, and in fact there's a couple different ways of doing that. One way is to go through an I2C chip that interfaces it, and this chip, their standard little piggyback module is already out there. It's called the PCF 8574. I2C chip, and basically it gives you 8 pins, so you can send an I2C byte out to this chip, and it'll drive 8 pins. 1 pin is used to turn on and off the backlight, and then the other 7 pins, 4 are used for the 4-bit mode on 4 of the data lines, and the other 3 are the 3 control lines: command, register select, read write, and the clock, the E line. So we typically do a 7-bit interface with in 4-bit mode, and then 1 bit to turn on and off the backlight. There are some, I think there are some SPI things out there, and then there's also, there are a few that you can buy that are set up as RS-232. We designed a little board which we had manufactured, and I made about 15 of them by hand, even though I do have a stencil, and I could pick and place them, but I haven't done that yet. But in any event, we made a little thing we called the Viva Blue Screen that has a Bluetooth module on it, and it has the firmware to take I2C, SPI, Bluetooth, or UART information and display it on its 16x2 7-segment display. And the board is exactly the same size display, fits on the back of it. And so I have some of those. If you want to use one of those for your projects, let me know. I'll be happy to let you do it. And you can even Bluetooth into it, which is really kind of cool. You have a jumper that, when you turn it on, the jumper sets the mode that it comes up in, and that's how that works. And then you just send it a vertical bar followed by 32 characters, and that they get displayed. The vertical bars for the Bluetooth. If you're just doing I2C, SPI, or UART, you don't have to have the vertical bar. There's a great document out there by Julian Iwat, who does a bunch of electronics blogs. Many of you probably seen some of his stuff. And here are the references for these two. If I click on it, it should come up. And so anyway, here it is. And this is a great read. So if you're going to use the LCD display, for the love of God, read both of these 2 documents. It's only, 16 pages for part 1 and another 8 or 10 pages for part 2. It's an easy read. And this is just great. It lists all the different sizes. It talks about how the pin outs can vary. This shows you the 14 pin out, but like I said, most of them have the 2 pins for the backlight also. He wrote this a long time ago when a lot of them didn't have backlights.
Professor,
but they all do now. What's that?
Excuse me, where is this located, this file?
It's on Blackboard.
Where, yeah.
Yeah, it's right here in content.
Okay, cool, thanks.
So if you go down to, let's see, well this is that was in my slides, but then they're on Blackboard too. But if you go back to the root directory, and then you scroll down here, you'll see LCD files and LCD instructions. The LCD files have the firmware and the header files for you to go ahead and use a parallel or a serial hookup. And the LCD instructions, these are the 2 Julian Iwat files right there, part 1 and part 2. So they're there. They look a little differently here for some reason. I don't know if they reformatted it. This is what the original looked like. So same idea. Anyway, but it's a great read, so you should definitely read that. I encourage that strongly. Okay, so anyway, for some reason I couldn't copy the thing out of the Julian Iwat article, so I copied this one, but I don't actually like this one. But I'll show you my other thing in a second. Well, maybe yeah, so here's what the Julian Iwat looks like. It's actually, makes more sense for some reason. So these are the commands. So there's a clear display command, there's a display and cursor home command, there's a character entry mode, there's a display on, off, and cursor command, there's a display/cursor shift command, there's a function set command, and then there's a set the character generator RAM address and set display address. Those are the commands, and these little keys down here tell you what these little characters in here mean. And so there's this, it takes a little figuring this out to get the lines right, but there are examples in the example software that kind of do it for you. And then once you get everything running, the rest of it's real simple. You either send characters or you might reposition the cursor or that sort of thing. If you want to move the cursor around, you have to go in command mode, and issue a display address command. If you want to send data, then you put it in data mode, and you just send the ASCII value of the character. And you can see what characters are going to be displayed. I think they're here. I have those on that data sheet, so let me see. Let's go back to let's see. Escape on my computer. So if I get out of this, and I get out of this, and I go back to the web, close it. So, yeah, if I go down to those articles, you'll see. So you just scroll down to where it talks about these articles, LCD instructions. And if I look at part 1 here, here it is. Yeah, maybe I'll download it. So all right, so anyway, if we look at this, so here's a little setup. You can actually buy one of these displays for $2 or $3 on eBay, and you can set up your own. You can get a bunch of switches, and you can actually play with it just like I'm going to do in class, which is kind of instructive and interesting. But because of debouncing problems, unless you do a little debouncing, you'll actually be kind of frustrated trying to do this. I did try and do this, and I never really got it to work. I thought every display I bought was broken. Turned out they were all fine. Too many problems to make it work right. It's much better to control it with a microprocessor. That's what it's made for. And here's his setup like this with his little dip switches and his little hex wheels. But, you know, great. I didn't have that luck. So here are the commands again. And here's he made a little circuit to debounce it so he could do this mechanical thing. Just hook it up to your Viva board. When you send characters, this is how this is interpreted. So you have 255 characters you can send, and this tells you the whole schmear, actually 256. So some of them are the character generator RAM. So that would be this whole row here. These you can program yourself. And then I guess there's nothing in this row and nothing in these two columns. And then you can see there's this I don't know if it's hiragana or katakana, but anyway, these Japanese symbols. Does anybody speak Japanese? All right. And then there's a few other, there's some Greek letters and some other stuff you can use. And then over here, the numbers, punctuation marks, and upper and lower case, the full ASCII character set. So it's all there. So, but you can define up to 16 of your own symbols, and you have a 5x7 matrix, and you get to turn the dots on or off. And there are instructions in this document how to do that, and we've had students do that. It's pretty cool. Okay, so we'll leave this kind of alone for now. Well, so, let me show you one other thing. Let me go back to that, actually. So, what's interesting to me is the number of different form factors this comes in. So, if you look at this, you'll see, notice we have, this is kind of the standard 16x2 line display, and then we have, so you can see they come like this, and then, but you can also get them in some different formats. This one is probably 2 by 20, so 2 lines, 20 characters each. And here's, I don't know what this one is. This might be 4 by 16. The most you can get is 4 lines of 20 characters. They even have some big long ones like this that might be 40 characters long by 1 line, or maybe 2 line by 40. They come in a number of different formats. What's interesting though is the way in which these are numbered is sort of it's kind of goofy. And so because it's kind of goofy, that's in this document. So this tells you how they're numbered. So this is the standard 16x2 display. That's what I'm going to demo here in a second. Notice it starts with 00 to 0F. 16 across, 1 line. But the next line down is 40 through 4F. It's not 10 through 1F. It's 40 through 4F. And then here's a 20 character line. So notice it goes 0 to 10, or whatever that is. No, it goes 0 to 9, and then 40 to 49. Kind of crazy, right? Why they do that, I don't know, but that's what they do. And then here's a 2 by 20, so that goes 0 to F, and then 10, 11, 12, 13. And then this one goes 40 through 4F, and then 50, 51, 52, 53. And then here's the 4 line. So one line is 0, this is 4 line by 16, so it's 0, 40, 10, and 50 in that order. Kind of crazy. And then here's your 40 by 2, and it's all, so if you want to put the cursor here, you have to kind of refer to one of these documents to figure out what the number of that position actually is. If you put the cursor, like you have a 16 by 2 line display, and you set the cursor to maybe 10, well, you're not going to see it because it's off the screen. It's still legitimate. It will write the character into that location, but you will display nothing because that's not one of the active display positions. And the way these work, it's really kind of interesting. I should bring one that's broken apart. But this is a liquid crystal piece of glass, and it's connected to the printed circuit board with this elastomeric material. So there's a circuit and active components etched onto this LCD, and then there's this elastomeric tissue that actually does the connection, and then there's this real strong metal bezel that sticks over the top of it. And if you look at this, you can see, I think, somewhere I have that flipped back and forth. Oh yeah, here. If you look at this, notice on the back side of this that you have these little metal bent things. These are the pieces where the bezels push through the printed circuit board, and then these little tabs are bent to hold that bezel in place. The reason for that is it actually pushes the glass, the liquid crystal glass, down on to that rubbery elastomeric tissue or material that's then makes contact with the printed circuit board. And the printed circuit board has, it sort of looks like this. And on the actual printed circuit board, there are all these little bitty contacts all along here to drive the display. And then you have this piece of elastomeric tissue, material, that's kind of a little chunk like this. And it sits on top of there, and then the glass sits on top of that. And there's a little chunk of this material on both sides. Can't draw very well. And that bezel holds it all together. So if you untwist those tabs and peel off the bezel, your display will fall apart. You can put it back together, it should work fine. And if you look at this elastomeric tissue, material, I don't know why I want to call it tissue. Anyway, what it really is made up of is teeny little slices of a teeny little, very, very thin insulating material sandwiched with a very, very thin layer of conducting material with a very, very thin layer of insulating material. So that when you put it on here, it works out that every one of these little pads is effectively connected up to the underside of your LCD glass. And they're little teeny pads, I guess they're little silver electrode pads or whatever, actually on the glass itself. When they manufacture the glass, they put that on there to connect it. And that's how it makes electrical connection to the liquid crystal glass. So it's kind of cool. And if for some reason it screws up because your bezel gets loose, you can actually fix it. But sometimes, over time, this elastomeric material will harden, and then it kind of stops working properly. So sometimes that's a problem. Okay. All right, so we can interface it a number of different ways, and then we talked about the article, and then here's the command. So let me demonstrate it. So I think I'll go over. Well, so let me fire this up. All right, so we'll bring the waves thing back up. Okay, so first I'm going to turn on the power supply. Now you'll see when I turn this on, you'll see that the display comes up in a single line mode. Now, what's really interesting is, it's a little crazy, it comes up, whenever you power the display on, it comes up with the display itself turned off. Now the backlight's turned on simply because I'm powering the backlight. I can turn the backlight on or off. You can still see the display with the backlight on or off. And if I go into to my little Waves program here, and I think the backlight's driven over here by this supply. So if I actually turn this off right here, you can see the backlight will go off. But actually the display's still there. You can still see the display. But the display is actually off, even though you're seeing that funny pattern. And you can also see, you only see one line. It's not in two-line mode. So I'll turn this back on, the backlight back on. So now you can see that. And notice if I change the reference voltage, so I have a little reference voltage here, where I can flip that around right here. So it's currently set on 600 millivolts. But if I click in there, and then I run my cursor down, I'll decrease it so you can kind of watch here. You can see, well, it changes this display. And at some point, it just goes away. I think I'm up to 4 volts now. That's quite a bit. But there's 3 volts, 2 volts. So at 2 volts, even 1 volt, it pretty much disappears. And then as I get closer, and it gets, you kind of get the best reading. I found earlier it was about 600 volts was the best. Millivolts, 0.6 volts, not 600. Okay, so anyway, so I'll turn this, I guess it is, oh, it's on now. All right, so if we go back to here, so that's the power supply stuff. And then this just powers the chip. So the chip is powered, the backlight's powered, the contrast is set to what I already figured out was optimal. But you can't see anything because the display's off. Now what they recommend, and if you read completely through that Julian Eilert article, you'll see, and I think you have to read they're two files. You have to read both of those. Like I say, maybe 25 pages max. When you read through those, you'll see that they recommend a certain procedure for turning on the LCD display. Because when you first power it up, it depends on how fast the voltage rises, whether or not it goes into a dysfunctional mode or not. And so the only way you can be confident your instructions are going to be properly received is you have to go through a proper initialization protocol. And the protocol is to send it the command 30 hex 3 times. So I'm going to do that. I'm going to send it 30 hex 3 times. So here's my 8 bits. Now, I have all 8 data pins hooked up. I will use it in 8-bit mode for a while, and then maybe at the end I'll put it in 4-bit mode and just show you how that's supposed to work. Because normally, when you hook it up to a microprocessor, you really don't want to do 8-bit mode. It is simpler, but it wastes a lot of your GPIO pins, and it may waste so many of them that you won't be able to get your project, be able to do the rest of your project. So a lot of times, we'll want to use it with a minimum number of pins. You might even want to go and use it in I2C mode, because in I2C mode, it only takes 2 lines, and you can use that I2C line for something else. You can actually have well, in theory, you could have 100 things hung out there on your I2C line, 100 different slaves, this just being one of them. So it's kind of cool. So anyway, so what I'll do is I'll set this up. So I want to put in 30. So this is 30, okay? And so now I'll do that, and I'm going to hit the E button, so I'm going to basically clock it 1, 2, 3 times. Now if you look at the display, nothing's changed, because the display is still off, which is kind of strange, but it's still off. So the first thing now we're going to do is we're going to go back and we're going to turn it on. And to turn it on, we have to send the command 0F, okay? So I'm going to do that. Now in 4-bit mode, you can actually do this a little differently. The first thing you do is put it in 4-bit mode, and then you would send 0F, because you don't have any connection to these lower 4 bits. But we're in 8-bit mode, so we don't have to do that. We'll just send the command 0F. Boom, done. And what I want you to see now is it's changed a little bit. See how the initial position is blinking, and if I adjust my contrast a little bit, I don't know. Oh, it's not in two-line mode. Oh, never mind. One thing you'll see, I can make it look better if I adjust this. Okay, see, that's better. But that adjustment is 900 millivolts. Well, 900 millivolts doesn't look quite as nice in two-line mode, but it looks better in one-line mode than 600. So if you're going to run in one-line mode, you may have to change, and then two-line mode, you may have to screw around with your contrast voltage. But in this case, I'm going to dial it back to 600 because we're going to go to two-line mode here in just a second. And so that's what I want to be. Okay, so here we are, back in our little controller. Now, to get it into two-line mode, I'm going to put in the command 38. So this is 3, and the 1, and then 3, and these are zeros. That's 38, and we'll hit it, and now we'll see that you can actually see both of the rows. If I change that contrast, you can see the rows more clearly. I may have to go up a little bit. No, actually it looks pretty good, so I'll just leave it there. Anyway, so there it is. And when you first turn it on, the memory is cleared. It's displaying the space character for every location. And so space character is nothing. All right, now let's say I want to put in a letter. Okay, so to send an actual letter, I have to switch one of my control lines, my register select line, into the data mode. So now I can send characters to be displayed rather than commands to be executed. And I'm going to leave my read-write button down here in write. I'm not going to read it. And so, and I happen to know that if I send 40 hex, or 41 hex actually, that's an A. So I'll send 41 hex, and it should put an A on the screen. So I'll send one, and then I'll send a couple more, but I'll let you look at it. So you can see we have a nice little A out there on the screen. And then every time I hit my little RS button, I keep sending out A's. Now notice, guess what happens when I get to the end? Okay, so I send another A. That's the last one. Now I'm going to hit another and another and another, but you're not seeing anything change because I'm writing now on 20, 21, 22, 23, and they're not displayed. In fact, if I keep hitting this, eventually I'll go all the way through the 20s and the 30s, and then finally I'll get to 40, and look, it pops up on the bottom line. So if I want to write on the bottom line, I usually have to send a command to position the cursor on the bottom line. So let's look at that. So, so to get the command, well, first off, let me clear the display. So I'll go back into command mode, and then I'll look over here. I'll look over here at my table. So let's see, clear display. So it looks like for that I would use 000000001, R hex 01. I can also clear the display and move the cursor to home with hex 02 or 03. So I'll just do hex 02. That'll be nice. So I'll go to hex 02. I'm in command mode. So that's 02. And then we'll hit that. Let's see, I'll let you see the display. All right, and I'll punch the E button once. Now set the cursor to home, but it didn't clear it. Now to clear it, I have to go to hex 01. So I'll do that. Hex 01 is here. And then I'll hit the E button and go back and let you see it. And it's all nice and clear back to where it started. Now let's say I wanted to write on the bottom line instead of the top line. Well, now I need to position my cursor. So I look at my set of commands again. Okay, set display address, so that's right up here, set display address. It's a 1888888, 7 bits of A. It turns out my display area is roughly 128 locations, although it's not quite. And so I can set this, I'll set this display address then to 1, and I happen to know the bottom line is 40. So that's going to be 1000000 with a 1 up here in the D7 position. So basically, I'm going to write 11000000, which turns out to be hex Charlie 0. Okay? So I'm going to put in C0. So I'll go back to my command, and I'll put in C0, and then I'm going to hit this, and what it should do then is set the cursor on that bottom line. So before I punch it, I'll let you guys see the cursor. So I'm going to punch the E button now, and there it is on the bottom line. And now, if I go back here and I change this around to display, I'll put a B. So a B would be 2. Instead of 41, it's 42. And then I'll go back here and let you see that. Hopefully it'll be a B. Oh. Oh, it did a space. Let's see. Oh, okay. The reason is because I got in a hurry and I'm still in command mode. So Lord knows what I just did. I may have changed a bunch of settings. So what I'm going to do then, hopefully I don't have to do anything. I'll just change this to data mode, and hopefully that'll work. But sometimes you screw things up, and then you got to reset it and start over. Yeah, it's not happening. Let's see what happens there. All right. Crap. So what I'm going to do, I'm just going to give it 33 times. Whoops. This one. Oops, I'm still in data mode, so I can't do that. Okay, 1, 2, 3. And then I'll put in 38. Well, actually, I'll put in 0F. Let's see if we can get it reset. Sometimes you have to power it off and back on. You do have to be careful not to give it bogus commands. Sometimes it's not very well behaved. Okay, you can see it's kind of looks like it's sort of reset. I hope. Okay, so now I'll put it in 38. All right. Yeah, okay, that's kind of good. And then, all right, so I think I'm probably okay. Let me just for granted see what happens if I try and put in a letter. All right, I'm going to power it off. It's just how it is. All right, so back to command mode. 33 times. So when you write code for this, you want to make sure you remember whether you're in data mode or command mode. Okay, and then we'll do 38. All right, and that looks good again. All right, so now let me just put in an A on the upper line just for grins. All right, so we're good. All right, now I'm going to set the cursor to the bottom line, and then I'll write B's on the bottom line or something like that. All right, so I put it back in command mode, and I want to put it into command mode. I know the bottom line is C, the top line is 80, and the bottom line is C0 hex. top line's 80 hex. So here's C0. So that should put us in the bottom line, and it does. And then if I wanted to go back to the top line, then I would put in 80 hex. And you can see that does that. Now I'll go back to the bottom line, and I will write something on the bottom line. Okay, there we are on the bottom line. Now I'm going to switch it into letter mode, and I will write in B's maybe. So that's, I know that 41 is A, 42 is B. So there it goes. And there. And you can do whatever you want, basically. So it's very cool. If you just keep going, you'll eventually wrap back around and go to 1 once you get past 60 or whatever. I'm just clicking away here. And eventually, now I'm writing and starting at 0. So the display wraps, but that's not very useful. Really, you want to, what you typically want to do, so like if I wanted to rewrite this, I should normally shift into command mode and put in the command 80, and that would put me back to the beginning of the line. And then what I would do then is I'd overwrite that line with whatever the data I wanted there. Maybe I'll put in C, I don't know, I'll put in some other character here like this one. Yeah, D. So you can see that's kind of how that works. So it's very cool, but you have to control every single bit. Now if you're going to do 4-bit mode, it's a little different. So what you have to do in 4-bit mode is you have to you do the same thing. You give it 30, 30, 30 a bunch of times. So I'll turn it off. Well, actually, I think we're okay. I'll just go into, well, I'll start from scratch. So I'll turn it off, we'll turn it back on, and then I'll go back in command mode. So I do the same thing. Now, remember now, we only have 4 bits, right? But we're powered up in 8-bit mode. So our bottom 4 bits don't count for anything. What I'm going to leave them, I'm going to leave them to 0. But really, that's not fair. I should just high Z them, I guess. But anyway, I'll set them to 0. You can ground them if you want. That's legal. Anyway, so here they are. So the first thing I'm going to do is I'm going to put in 30, and I'm going to give 30 issue 30. So because the bottom bits hopefully are grounded, they might be high Z. Usually we pull them down though, and we normally don't connect them to ground because what if you want to read the display? Well, when you initially power it up, you might be driving these pins, and so you're probably best to pull them down and not ground them. But anyway, here we are. So we'll just leave them grounded here. And then what I'm going to do is I'm going to go ahead and hit 30, 1, 2, 3 times. That's the standard way of bringing the display up, so it should be properly interpreting commands. Now I want to go, the first command I want to give it is to go into 4-bit mode. Well, how do I do that? Well, let's look. So if I go to this chart over here, I should be able to figure it out. So if I look at the chart, notice I have 8/4. A 1 in this position is an 8-bit interface, and a 0 in this position is the 4-bit interface. And that 8/4 is right here in the D4 location. So what it's basically saying is, I can write in the command 0, 0, 1, 0. And then this other stuff doesn't really matter. It'll be set as zeros or whatever it reads. But what it'll do is put me in 4-bit mode. So that's what I'm going to do. And once you go into 4-bit mode, now every other letter and every other command has to be sent in 2 4-bit nibbles, or you'll get out of sequence. And so when you write your code and use your code, make sure once you go into 4-bit mode, you don't accidentally put it back into 8-bit mode, and then you can't understand why it's not working correctly. Or you send 1 character, and then you send 2 nibbles the next time, and then 2 nibbles and 2 nibbles, and you don't realize you're actually 1 nibble off. So anyway, so you just have to keep your head screwed on pretty good about that. So so here we are. So I'm going to send in 0, 0, 1, 1, don't care, don't care, don't care, don't care, and that's going to put me in the 4-bit mode, right? So, and the other things, this 2-1 or 1-line mode, I don't know how those are going to come out. I'm going to have to do that separately as 2 4-bit nibbles again. So here we go. So I'm just going to go ahead and click this once. I'm in, so I have it set up here, right there. And so when I click it, it's you don't really see much happening. Now if I want to go ahead and issue some of the other commands, like go to 2-line mode and start my cursor. So notice here we've got some other things. The first thing here is this. Sorry, let's see. So I want to first now I want to turn the display on. I can't turn the display on until I get it into 4-bit mode, because I have to write these lower 4 bits to do that. And I'm unable to access these lower 4 bits when I only have 4 wires connected, because my 4 wires are connected to my upper 4 bits. So I have to first put it in 4-bit mode, and then I can start issuing these other commands. So the first other command I'm going to issue is I'm going to issue to turn it on, and I'm going to send it. Now, do I send the high nibble first and then the low nibble? And the answer is yes. I send the high nibble first and then the low nibble. So I'm going to send 0, 0, 0, and then I'm going to send 1, and then my D here is going to be display shift. I'm going to do, so it's going to be 1, where is it? 1, 1, and then the underline, yes, 1, and B, yes, 1 for blinking. So U is underline cursor, B is blinking. And it's nice to see that blinking cursor. Now, in some applications, you might not want that, that's fine. But for what we're doing, I want you to see where the thing is, so I want it blinking and stuff. So I'm going to do 0F. But first I have to send the 0, and then I can send the F. All right, so here we are. So first I'm going to send the 0, and I have to use the upper 4 bits. Forget these, they're totally out of the picture now.
Dr. Morton,
Yeah.
whenever you set it to 4-bit, should it have been 0010 and you set it at 0011?
No, it should have been 0010. Did I send it 0011?
0011.
Oh, okay, that's good. Well, I better fix that. So I'll set it 0010. Yeah, because it is, yeah, you're right. 4-bit mode is 2x. Okay, yeah. All right, so I'll do that. Now it's in 4-bit mode. Okay. So now I'm going to send the upper nibble, which is 0, and then I'll send the lower nibble, which is F. So, yeah, thanks for pointing that out. Otherwise it wouldn't have worked. Now you can see, I get a blinking cursor, but it's still in 1-line mode. That's because to set it in 2-line mode, I have to go down here to another command. So I have to use this 2-line mode here, 0, 0, 1, and then I have to make sure I put a 0 there, or otherwise I'm going to screw everything up. And then I want 2-line mode here, so I'll put a, let's see, 1 is a 2-line mode. So I want 0, 0, 1, 0 for my first nibble, and then I want 1. I want to put it in 5 by 7, so that's a 0. So 1, 0, and then don't care, don't care. So I want 2, 2, 8. Yes, I want 28. Yeah, 28. I don't know why I didn't have that written down. But anyway, I do want 28. Pretty sure. So let's do that. So let's go here. So the first thing I'll do is I'll put in 2. And remember, if I somehow put in 3, I'm completely screwed up now, because I'm no longer in 4-bit mode, and now I'm sending both commands at once, but I don't think I am. So that's A, or say the letter B at the bottom row. Now I have to shift into command mode, just like before, and I'm going to write in 40. I'll say 42. So there's 4, and then 2. And that should be the B, and it is. Okay, so anyway, So without beating the horse to death, that should give you a pretty good feel for how this works. So, all right, so let me stop there and see if there are any questions, and now I want to show you a couple other things. Yeah.
4-bit mode, it just takes the first nibble and just waits for a second one?
Yes. Yeah, there's no requirement for how fast you have to do it. I mean, in your micro, you're probably going to do it within a few millionths of a second. But there's really no requirement.
So if we just get random stuff, we probably mismatch nibbles or something like that.
Well, I mean, if you start sending random data, you'll get random stuff, yeah. And if you send random commands, Lord knows what you'll get. But probably you'll inadvertently go out of 4-bit mode and into some other mode, and then you'll be out of sequence, so you won't know whether you're sending 4 bits or whether it's taking your 4 data bits and 4 garbage bits as an 8-bit byte each time. So it gets real, you have to be careful when you use this display, otherwise it won't work. But if you do it carefully, it works great. And it's pretty reliable, but you will find if you don't do the 30, usually what you should do, power it up, wait about a second for the power to be up. Because you have to remember, this is a device, most of the time it has a response rate of about 40 nanoseconds or something. So it's pretty fast. But when you issue the clear cursor and set it to the home position, that can take up to something like 38 milliseconds to run. So, or is that right? No, maybe it's 38 microseconds. That's all described. But anyway, it can take a significantly longer time. And as a result, it's always good to put a little time delay in before each command. And then if you know you're going to issue one of these longer commands, and this gives you all the, if you scroll down to that Julian Eyelet document, it gives you all that information's in there. When you're going to issue a longer command, you have to put in a longer delay. Now, in one of the programs, the software I gave you on the web, you can read the busy bit and it's going to make those adjustments automatically. But in the other one, it doesn't read the busy bit and you have to program your own delays. So you just have to always pay attention. And if it's not working, then you might want to add a little delay. Maybe you're trying to drive the display slightly too fast. But it's pretty quick. Generally, the micro can, about as fast as you can format the letters and stuff, it'll probably take the data. And especially if you're driving it with I2C, it's way slow enough, not going to be a problem. But if you're doing it with a parallel interface, yeah, you might overdrive it then. All right, any other questions about that? That's a good question. So it's interesting, right? So on one hand, it's very powerful. On the other hand, it takes a lot of details to make it work. And that's just kind of a theme for microprocessors and embedded designs in general. Everything you do, generally you can do very powerful things, but it's a bit at a time, right? One bit at a time. And so that means it's a lot of work on your part. That's why you get paid, because it is a lot of work. And not everybody's smart enough to figure out how to do it. A lot of people are way too impatient to take the time to learn how to do this. So that's why you'll get paid. Okay, so let me show you a couple other things. Unless any other questions on this, I think that's really all I wanted to say about that. We're good? Okay, so I wanted to show you the OLED display, because it's kind of cool. So here is one. Now what's interesting is, I'll just fire it up and let you see it. So anyway, so we'll turn it on, and so you can see, I put a little road runner in it for the splash screen. And then it comes up. Now so it's nice because it's graphical and you can do a lot, you can do stuff on it. It's not very big, but they're fairly inexpensive. That's one thing that's really nice. And here, it's interesting, our camera's showing us, to my naked eye, I don't see it flashing, but the camera does. So it's kind of cool. And so you can see it's up. To configure this display, so this is set up with an I2C interface. They come in other ways, SPI, and I don't think there's no direct interface because there's a lot of pins connected to it. But in the I2C interface, it's fairly nice. You have to send, I think there's about 38 registers that must be configured properly to make this display work. So you have to write 38 bytes out to the display before it'll do anything. And if one of them screwed up, it won't work right. And some of them will do things. You can scroll the display one way, the other way, left, right, up, down. You can change their voltage issues on here. You can change. It's very complicated. So generally, I just kind of use the standard configuration registers. But if you wanted to play with them, you can get some special effects and stuff. And then the other thing is, this display does not recognize ASCII characters. So you have to have in your program built-in fonts that it can recognize. And then it takes those built-in fonts and you give a character, and then you call the font routine, it returns the bit pattern, and then that's what gets written out to the display. Now the splash screen takes a whole 1 kilobyte of memory to store the splash screen. And you can get a special editor and you can edit up your own splash screen. It's just a BMP image, and then there's a special piece of software that converts it, and then once it's converted, you just put it in your program. But I have a question. So how much RAM do we have on this chip? 1K! Oh, wait a minute. I have a 1K splash screen. How did I do that? Yes, I put it in program memory. And if you declare it as a constant, so a constant const int. So if you declare that as a constant int, so then it'll work. If you declare it as a static int, it won't work. And then you just paste that code, you paste the pattern, the ones and zeros you just paste in so that it sets it equal to that. You just do equal. And I think you have to put brackets. And then you put all the bytes. And then you put a closed brace. And that's it. And you have 1024 of them. You have 1K of them. And then you can write that out to the screen all in one fell swoop. Yeah.
How many characters by how many characters could you really
So it's 128 pixel dots by 64.
Oh, perfect.
So 128 by 64. So the each dot is a single bit. It's either on or off. There's no grayscale. There's no color. So it's either on or off. Now they make a lot of these displays the first 4 or 5 rows are a different color. And I don't know if they put a mask over them or what they do, and then the rest of it's a different color. And if you have one like that, then you can use this for a special title bar if you want. It's kind of cute. But you can't change the color. It's just that it's set up with a different color in the top 4 rows or 5 rows or 6 rows, whatever it is. And then you can get different fonts. So I went out and stole the font, and you also have to put there's a bunch of data for the font. So the font has to be stored also as a constant, as a constant int. Or so actually, not an int. Char. You want it to be 8 bits. So constant char. So you also have to store your fonts that way. And then if you want to create graphics, you can do that too, but you have to have functions that generate the bit patterns. And that stuff's all out there and available, but you have to go import. You have to go find it and then import it so it'll work in your code. But I'll put some standard. But if you want to use one of these displays, I'll put the standard driver on, and then you can go from there. I did want to take just a minute and look at the software. So let's do that. So if we get out of here. And again, if you want to use one of these displays, and you're welcome to, make sure you read those 2 Julian Eilert books. Okay, so if we go back to our web, so here are the 2, part 1 and then part 2. here's what part 2 looks like. It's basically the same thing, it's just part 2. And he goes in, he talks about the timing diagram, you can see here, in a 4-bit mode. He talks about the execution times. Yeah, okay, so here are the actual details. So character entry, so most commands take 40 microseconds. The read command to check the busy bit takes 1 microsecond. And then, but some of the commands can take up to 1.64 milliseconds. So you do have, so if you get a 2 millisecond delay, you'd always be okay. But that would slow things down a little bit. But if you know you're going to issue one of these display and cursor home or clear display, these 2 commands can take up to 1.64 milliseconds. And that depends on whether you're 2 line by 16 or 4 line by 40 or 4 line by 20 or whatever you are. All right, and then the busy bit, it talks about the busy bit if you want to do that. Like I said, I've implemented on one of the things, I tried to implement the other, and it's gotten bugs, so I took it off. And I have to go back and read this. It's kind of fairly complicated to figure this out. It's not impossible, but just have to read through it and figure it out. But the high order bit, and I believe it goes to a 1 when it's no longer busy. It probably says there. Yeah, I don't know. Anyway, so somewhere it says, I don't see where it says. Anyway, so that's the other half of the document. So you should read both of them. Now, if you go down, if you scroll on down or up, you'll see LCD files. So here are the files. So there are 5 files out there, and I'll also put the file for the old LED display. Okay, but remember, the OLED display won't work with the LCD display. Anyway, so there are 2 files for parallel. So in the parallel configuration, you take your microprocessor and you have to hook up at least 6 pins to your LCD display. 4 data pins, the E line and the RS line. You can ground the read-write line. You can put a pot on the contrast pin, and you can pull down or just leave unconnected. Although you should pull down the lower 3 nibbles, the lower 4 nibble, the lowest nibble, the data 0, 1, 2, 3. Okay. So that's called the parallel interface, and then there's code. So here's the code right here, and you can modify these things to display what you want to display. There's a header file to include, and then there's an example program that uses the header file and actually makes it work. The other thing you can do is get the LCD display with the little board on the back of it that has the I2C chip on it. And then you can drive it that way. And for that, you need a header file for the ICD code, the I2C code, a header file for the I2C/_LCD driver, and then a little sample program to show you how that works. And so that's all out there for you. I think on the LCD, on the I2C code, I do read the busy bit. On the parallel code, I don't read the busy bit. I forget why. Or maybe it's the other way around, I can't remember. But anyway, so that's it. If you want to read the busy bit, you have to connect the read and write line and switch it to read mode. But if you don't care and you just throw in a fixed timing delay, that's fine. All right, so that's where that code is. It takes a little bit of working with it to figure it out. I mean, this should run out of the box, but then when you start modifying it, you can find it is glitchy. So if you have problems with it, let me know. I'll be happy to help you. All right, any questions about the code or LCD displays? All right, we will see you on Thursday.
Yeah.